Hello? Hello? Greetings. Are people able to hear me? Hello, are people able to hear me?
Yes.
Yes.
Okay, excellent. So it looks like we've got audio. Excellent. I'm going to switch to sharing my screen. Okay. So before we start, any questions from the last time? Okay, and then again, if there are questions you have, we do have a couple of undergraduates who are happy to chat with you about stuff. So what I want to do today is I want to continue with some of the general background, and the goal is to show you a couple of different types of problems one can ask in the field. And then by the end of today, we'll start talking about one area that I think is very ripe for new investigations. And what I like about the problems is a lot of it is not going to require too much advanced machinery, too much advanced mathematics. So I think you'll have some real opportunities to contribute. Now the question will be at the end of the day, are you able to get a nice result and prove it, or will it just be an observation? If you're able to prove it, that's wonderful. If not, it's at least the first start in research, is trying to figure out what do we think might be true. And then it might take a while before we end up with a proof, or it might not even happen with us. It might happen in a subsequent year, in a subsequent class. A lot of the stuff from later today was proved in last year's program, but it actually began a few years before that when I was on sabbatical and teaching at Carnegie Mellon. And I was working with a student, Joshua Siktar, who was helping me last summer and is available to help some of you this summer as well. And it took a couple of years before we found the right perspective. And so when we get to that problem later today, it turns out that just very recently at Carnegie Mellon, we're in the middle of writing it up, we found a way to push a lot of those results significantly further. But it does sometimes take a while. So what I want to talk about now is different types of decomposition problems. So when we looked at the Fibonacci numbers in the beginning, we saw that every number could be written uniquely as a sum of non-adjacent Fibonaccis. It turns out that this is an equivalent definition of of the Fibonacci numbers. What do I mean by this? So you normally define the Fibonaccis as 1, 1, 2, 3, 5, 8, and so on. And then this gave rise to the notion of a legal decomposition. Every number can be written uniquely as a sum of non-adjacent terms. You can go the other way around. What if I give you a legal decomposition rule? What sequence does it induce? What sequence does it imply? So let's say I want to write numbers as a sum of non-adjacent terms in my sequence. Well, what terms will I have? Well, I have to start off with 1. I can't have any number twice, so I now have to have 2. So I've got 1, 2. How would I get 3? Well, I can't add 1 and 2, so I would have to add 3. So I have 1, 2, and 3. Can I get 4 from 1, 2, and 3 without taking adjacent terms?
1, 3.
I'm sorry?
1 and 3.
Yeah, 1 and 3. Good, so I don't need to add anything for 4. Can I get 5 from 1, 2, and 3?
2, 3.
But 2 and 3 are adjacent.
Wait.
So can I get 5 using each number at most once and not using adjacent terms?
You can't.
Yeah, you can.
So my sequence is now 1, 2, 3, 5. Can I get 6?
Yes.
Yeah. Can I get 7?
Yes.
Can I get 8?
No.
No.
No. So the next term in the sequence is 8. So I'll leave it as a nice exercise for you to show that this is equivalent to the dimension of the Fibonacci's. It gives you the same sequence. Fibonacci's are the unique sequence such that every number can be written uniquely as a sum of non-adjacent terms. I'm sorry? One of the things you find as you go further and further in mathematics is that a lot of things have multiple formulations. And depending on what you're looking at, sometimes one formulation is more useful than another. Now, the Fibonacci's, it's a one-dimensional sequence. I can view them on a line. So a lot of the work today was inspired about trying to make things two-dimensional, to come up with something in the plane rather than something in a line. And I'm going to show you something that does look two-dimensional at first, although it turns out you can convert it to a one-dimensional sequence. And you can lose a lot of the geometry.
Professor Miller,
Yes.
can I ask a question you just mentioned? Like, you mentioned that 5 cannot be decomposed into like the sum of two non-adjacent numbers, like Fibonacci numbers. So is it against the rule of Zeckendorf like decomposition?
Well, what we're doing now is we're starting off with this rule. I want to construct a sequence such that every positive integer can be written uniquely as a sum of non-adjacent terms. Is there such a sequence, and if so, what is it? I have to start off with the number 1. Then I need 2. Then I need 3. And then we don't need 4. And then the only way to get 5 from this, well, we can't, because I can't use 2 adjacent terms, so I have to add 5 to my sequence. So if you use this as your rule and you start generating your sequence term by term by term, what you generate is the Fibonacci numbers.
Oh, I understand. Okay, thank you.
So it turns out this is another equivalent definition of the Fibonacci's. This is not defining them in terms of a recurrence relation. Normally we say each Fibonacci is the sum of the previous 2. Here, our definition of Fibonacci's is coming from decomposition.
Okay.
But it turns out the 2 are equivalent. So here is one generalization of the Fibonacci numbers. We call it the Kentucky sequence. It has 2 parameters, S and B. So we're going to look at bins of length B, and here's the rules. You can't have 2 elements in the same bin, and if you have elements from one bin, you can't take anything from the first S bins to the left or the first S bins to the right. So if you think about the Fibonacci numbers would be the 1, 1 sequence. Each bin has length 1, so you can't take 2 elements from the same bin. Well, there's only 1 element in a bin, so that condition is vacuous. And then if you have a bin, you can't take something from the bin before or after. That means you can't have 2 consecutive bins chosen. So one of the biggest things in mathematics is trying to find ways to generalize what you've done to something new. There's a lot of ways to generalize the Fibonacci numbers. We have each term is the sum of the previous 2. We could look at, well, what if you're the sum of the previous 3? What would that give you? Or the previous 4? Or what if you're the sum of the previous term and then 3 terms earlier? Or twice the previous and then the term before that? There's lots of different ways you can generalize. This way of generalizing the Fibonacci's is to come from the notion of a legal decomposition. And then we can ask, what kind of sequence do we get? The Fibonacci numbers satisfy a recurrence relation. Maybe there's a similar recurrence relation in this case. It's not immediately clear if there is, but we can hope and see. So as I remarked, the Fibonacci's are the sequence 1, 1. So the next simplest thing to look at is the sequence 1, 2. So because S equals 1, that means if we choose some bin, we can't have its neighbor. And now the bins have 2 elements in them. So let's start calculating the terms. And so I just wrote the first few. So the first bin is 1, 2. And so what I'm going to do is I choose each element to be the first number that I can't write using the previous stuff. So I've got to start off with 1. I then have to have 2. I can only take one element from each bin. So if I want 3, there's no way to get 3 from the bin 1, 2, so I have to add 3. There's no way to get 4, so I have to add 4. Now, if I want to get 5, well, if I choose anything from either the first or the second bin, I can't have its adjacent bin chosen, so I have to add 5. Can I get 6 from what I have here, taking at most one element from a bin and not taking 2 consecutive bins? So can we get 6?
Yeah, you just pick 1 and 5.
Good. Can we get 7?
2 and 5?
2 and 5. Can we get 8?
No.
3
No.
and 5.
Well, but are we allowed to do 3 and 5? If we did 3 and 5, we would have 2 things from adjacent bins. And we're not allowed to have 2 things from adjacent bins. So do we all agree that we can't do 3 and 5? It might be better to have the mutes off so that I can hear you. Do we agree that we can't do 5?
Yes.
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 Did somebody say no? Okay. So we can't do 3 and 5 because they're in adjacent bins, so we have to add 8. Maybe a sequence is just the Fibonacci numbers with 4 added. Let's see, can we get 9?
Yes, 1 and 8.
Okay, can we get 10?
Yes, 2 and 8.
Okay, can we get 11?
No.
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 No,
it's-
no.
So it's not just the Fibonacci numbers. We can get 12, 11, and 1. We can get 13, 11, and 2. Can we get 14?
Yeah, 11, 3.
Can we get 15?
11 and 4.
Can we get 16?
No.
No. Does anybody notice any patterns?
The second number, like, in each bracket is, like, power of 2.
Yeah, the second one is twice more than the second one in the previous. So maybe there's a recurrence relation going on here. The 1, 3, 5, 11 seems a little bit harder. Well, 3 is 2 more than 1, 5 is 2 more than 3, 11 is 16. It's looking a little bit more involved there. But sometimes the beginning is a little bit different. So if we continue, you can see we can get 17, 18, 19. How would we get 20?
16 and 4.
Yep. But we can't get 21. How would we get 31? Because we believe the next number we can't get is 32. So how would we get 31?
21,
Yes?
8,
Yes.
21, 8, and 2.
Yes. And in fact, the largest number you'll be able to get is you take the 21 and then you take every other bin and you take the largest element in each bin. And so it goes on and on and on. So we have a sequence. And with a little bit of work, you already noticed that A2n is just 2 to the n. And with a little bit of work, you find out that A2n plus 1 is 1/3 2 to the 2n, 2 to the 2 plus n minus negative 1 to the n. Or with even a little bit more work, it turns out that you can show that the A satisfy a recurrence relation. An plus 1 is an minus 1 plus 2, an minus 3, and then we've got some initial conditions. And because we go all the way down to n minus 3, we actually need 4 initial conditions. So one of the things that's different about this recurrence relation than the one for the Fibonacci's is the Fibonacci's was, fn plus 1 is fn plus fn minus 1. we don't have an AN term. It's 0 AN plus AN minus 1 plus 0 AN minus 2 plus twice AN minus 3. And it turns out that the first coefficient being 0 can often cause problems. Okay. So we do have a recurrence relation in this case, which is nice. We can plot the distribution of the number of summons. And so I chose 100,000 numbers randomly. And we get this Gaussian behavior that we had commented on before. It turns out this Gaussian behavior is a general result in most problems like this. Now here's a little bit more interesting stuff. I'm looking at a plot of the distribution of gaps for 10,000 randomly chosen numbers. So M has on the order of 60 digits. These are pretty large numbers. This is a strange distribution. It goes up and goes down. And what's really going on here is it's almost like two different distributions superimposed. So what I've done here, and again, this is just to give you a little bit of a sense of what's out there. At this point, do not worry about following everything. I just want you to see a little bit of the behavior. Do these plots on this page look easy to understand? Yes or no? I think these plots look pretty easy to understand. Yeah, they're basically straight lines.
Yes.
And what we're doing here is we're looking at essentially the ratio of even to even or odd to odd. And over here, it's really two different behaviors merged together. And so a lot of mathematics is trying to figure out how to view what you're doing. All right. So have you seen the Fibonacci spiral? This is something that my daughter, with a little help from my son, made a few years ago. A better way of phrasing the Fibonacci spiral is like this. Has everyone seen the spiral before, or is this new to you?
Yes.
I've seen it before.
Okay. So there's a beautiful theorem that's lurking in here. And the theorem is, if you look at the sum of the squares of the first n Fibonacci numbers, it's the nth times the n plus first. And here's a geometric proof of that statement. So if you look at the tiles, it's 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. So each of these squares, well, to calculate the area of the 34 square, it's just 34 times 34. The 21 square is 21 times 21. So if I want the area of this rectangle, it's just 1 squared plus 1 squared plus 2 squared plus 3 squared, and so on, all the way up to 55 squared. What's another way to calculate the length of, to calculate the area of this rectangle?
Length times width.
Yeah, length times width. And so the width is 55, and then the length is the next Fibonacci number, 55 plus 34, or 89. And so this is a geometric proof that the sum of the squares of the first n Fibonacci's is the nth times the nth plus first. And we're going to use this to construct a new sequence. And so there's two different ways of doing this. We're going to concentrate on the one on the left that has no holes. It looks somewhat similar to the Fibonacci spiral. The difference is, do you see how it's getting harder and harder to draw the spiral because the numbers are getting bigger and bigger and bigger? The next one would be 89. It's going to dwarf everything. So what we do with the image on the left is we have the length or the width, but just one of them being the correct size, and then we have it as just one unit. And we do it like this so that we can just compactify the drawing. You could draw it the other way, but it would take up too much space on the table. So we're going to try to create a new sequence with a new rule of illegal decomposition. And then we're going to fill in the numbers. And we're going to do it as follows. You can't use two rectangles that share a wall. This is going to be the generalization of you can't have two adjacent bins. You can't have two adjacent numbers. So we want to fill in the numbers. So we're going to start off with 1, and then we go down. We're going to do our spiral outward. We have to have 2, we have to have 3, we have to have 4, we have to have 5, because 2 and 3 are adjacent. We have to have, do we have to have 6, or can we get 6 using non-adjacent rectangles?
1, 5.
I'm sorry?
1, 5.
1 and 5 share a wall. We can't do 1 and 5.
2, 4. 2, 4.
2 and 4. So we don't need 6. There's no way to get 7. How can we get 8?
7, 1.
7 and 1. How else could we get 8?
5 and 3.
5 and 3.
So we've just seen that this has a problem relative to the Fibonacci's. We lose uniqueness. We can get every number, but some numbers can be written more than one way. We can't get 9, so we have to add 9. How could we get 10?
1 and 9.
1 and 9. Is there any other way to get 10? So I don't see any other way either. So some numbers become, now 11 we can do 9 and 2 or 7 and 4, then we get 12, and then 16, 21, 28, and so on and so on. And there's a lot of questions you can ask. You can ask, how many summons are there in a decomposition? Well, there could be more than one way to decompose. So you could ask, of all the decompositions of a number, maybe look at the one that has the fewest number of summons. That'll be K-min. Or maybe what's the average number of summons in a decomposition of a number? Or what's the maximum? Or what if we try to apply the greedy algorithm? The way we proved Zeckendorf's theorem the first time was we took our number and we threw away the largest Fibonacci number we could. Let's try to find a decomposition of 24. How would you try to find a decomposition of 24? Using this, what we'll call the log cabin or the Fibonacci quilt. How would you try to find the decomposition of 24?
21 and 3.
21, 3. Start off with the large number you could. What if you start off with 16? We get to 24 with 16. So 16 plus 9 is too much. We can't do 16 plus 7. We can't do 16 plus 5. We could do 16 plus 4 plus 2. We could get to 22. But no, that's it. So we can't do, there's only one way to do 24. But if we tried to do 22, we could do 22 as either 21 plus 1 or 16 plus 4 plus 2. Oh, wait a minute, I'm sorry, that would be 22, sorry. Yeah, right, so we can do 22 two different ways. One way has 2 summons, one way has 3 summons. So the number of summons of a number can actually depend on how you decompose it. It turns out the greedy algorithm does not always work here, but with a modification it will. So you can calculate what is the average number of decompositions. Since we're probably not going to go here, I'm really not going to go into the details here. I'll just say that you can find more recurrence relations. If you're interested, I can send you the paper. The arguments are not too bad. They don't use calculus. It's just counting. And you end up getting a recurrence relation of depth 9. And it turns out that the average number of representations is growing like some constant times approximately 1.05459 to the nth power. And so if it was, there would only be one decomposition. And so here, the larger you go, on average, the more number of ways you have to represent a number. And if you look at the greedy algorithm, you could ask, how often does the greedy algorithm give you a successful decomposition? And for small values, not surprisingly, it works 100% of the time. Well, because it has to. Your sequence starts off 1, 2, 3, 4. So if you start off with one of those numbers, the greedy algorithm, of course, is going to work. It gets more interesting as your numbers get larger. And you notice that, it goes from 100 down to 83, then 87, then 92. So it looks like it's rising, but then it drops to 91, then it rises back to 92.4, which is less than the 92.59. And so it turns out that, again, elementary arguments not using calculus, you can show that the number of times that the greedy algorithm works can be given by a recurrence relation. It's a little bit more involved because it has a constant term, but there are ways to handle that. And you can prove that in the limit, it's going to work about 92.6% of the time. All right, so I'm going to use, I'm sorry, was there a question? Okay, so we're not going to use too much of this, but I wanted to talk a little bit about this just to give you a sense of how we can try to bring geometry into the problem and try to come up with new ways of generalizing the Fibonacci numbers. And the way we're generalizing things is through this notion of a legal decomposition. Now, because these can be written as a nice one-dimensional recurrence relation, in some sense, it really is still a one-dimensional problem. And in fact, if I go back to what I had over here, I could write my sequence on the line in a nice way like this. So it's not really a two-dimensional problem, so we have to do a little bit more work. All right. So what I want to do now is I want to start talking about another type of questions you could ask. Gaps between summons. And we'll first start off by doing it with Fibonacci numbers, and then we'll shift to trying to find a two-dimensional analog that's really two-dimensional, that's a real two-dimensional generalization. And then the research problem I would love us to investigate this summer is going to be related to trying to understand the gaps of this decomposition. So this is a new problem. People have not studied this before. Last summer, people looked at it just briefly. We really focused on other things last summer. It will be interesting to see how far we're able to get. And with research, you do not know ahead of time, is it going to work or not? A lot of it is going to be a function of, can we find the right way to look at the problem? So a lot of these problems, if you look at them the right way, they're not so bad. And if you look at them the wrong way, the algebra is terrifying. It's also going to be a function of how much time you have. I know you are all busy with lots of different things, which is fine. But if you want to have new results, it is important that you have sufficient time to look at things. All right, so let's start talking about gaps. So here's a possible decomposition. So I go back to the Fibonacci's, and the R's are going to indicate which terms I have. So for instance, maybe I have F1 plus F8 plus F18. And what I want to do is I want to look at the gaps between the summons. And when I say gaps between the summons, I don't mean between the actual values F1, F8, and F18. I mean the gaps between the indices. How long do I have to wait from one summon until I get the next? So the gaps in this are going to be 7 and 10. Because it takes me 7 steps to go from F1 to F8, and it takes me 10 steps to go from F8 to F18. You could also talk about, if you want, the gap from the beginning to the very first term in your decomposition, but in the limit, you have to imagine having, say, 10 to the 4,000 summons. And then just waiting for that first summon, it doesn't really matter. You can just ignore that. It's not going to really affect any of the limiting behavior. And so the question is, what rules govern the decomposition of these gaps? So we're going to do a little probability here. So let's let P sub nk be the probability that a gap in our decomposition is of length k. So there's a lot to unwind here if you haven't seen probability before. The first is, P is coming from the word probability. The N is coming from the fact that we're going to look at numbers between Fn and Fn plus 1. And then what we're doing here is we're looking at every single number in the interval. For each number in the interval, we look at all of its gaps, and we see how often do we have a gap of length k. So k could be 0, it could be 1, it could be 2. It could get as large as, I think, n minus 1.
So Professor Miller, so it doesn't matter like the number of k gaps like a number have for its decomposition, right?
Well, so a number could have multiple gaps of length 5. And then every time you have a gap of length 5, you count it again. Absolutely.
Okay.
So, yes.
Just making sure k can be 1, right? Because if k is 1, then we can have f1 and f2, and they are adjacent. And
Right. So what do you think the probability is? Pn of 1. What do you think that is?
Oh, so that is just 0, right?
So that would just be 0. In fact, that was the question I was about to ask you. So well timed.
Okay.
What do you think Pn of 0 is?
0.
0. You can't use the sum in more than once.
0. So the probability is 0.
Right. Now, if we did decimal expansions, 2019, well, if we look at that, the fact that we have 2 in the thousands place means we have a gap of length 0. We have 1,000 and then 1,000 again. We have that summoned twice. Then we don't have anything in the hundreds, so the next gap would be length 2 to get to the 10 spot. And then we would have a gap of length 1 to get from there to the 1 spot, and then we would have a bunch of gaps of length 0 because we have a 9 in the ones place. But for the Fibonacci's, we know that Pn of 0 and Pn of 1 will both be 0. And the question is, does this limit exist as n goes to infinity? Is there a nice answer for what these gap probabilities are? It turns out the answer is yes. And again, you can ask similar questions about other expansions in other ways. So I talked about base 10. You could do base 2. So if I took 2012, that's 2 to the 10 plus 2 to the 9 plus 2 to the 8 plus 2 to the 7 plus 2 to the 6 plus 2 to the 4 plus 2 to the 3 plus 2 to the 2. So here we would have a gap of length 1, 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 a gap of length 2, and then another gap of length 1, gap of length 1. So I don't really want to say too much about this, just to say that in 2012, some of my summer students and I were able to prove what the probabilities are for gaps for a huge class of recurrence relations and legal decompositions. So the big thing is I mentioned that if the first coefficient is 0, problems happen. We need C1 to be non-zero. And if C1 is non-zero, we were able to calculate exactly what these probabilities are. If C1 is 0, things become more interesting and the algebra becomes more terrifying. So we could look at the probability of a base B gap distribution. And so the first theorem is that if you're looking at base B, then the probability of 0 is B minus 1, B minus 2 over B squared. And the probability of a gap of length K is some constant B to the minus K. So it's like a geometric decay. Well, if you think about it, when we're doing a base B decomposition, B has to be at least 2. So if we take B to be 2, this is a binary expansion, and then we're saying the probability of a gap of length 0 is 0 in base 2. Does that make sense? Does that surprise you? Or is that reasonable?
Reasonable, because B minus 2 equal to 0.
Okay. But why should the probability of a gap of length 0 be 0 base 2?
Because that would just be the next power of 2. If you have 2 same power. Right? Because
You're close.
so yeah, so if the gap is 0, which means that we should have, for example, like 2 powers of 2 to the like 6th,
Excellent.
and then that would just give us 2 to the 7th.
Excellent. We're not allowed to, well, you could have that, but we're not allowed to have, two copies of 2 to the 6th. When you do things in binary, your digits are just 0 and 1. So we can't have a repeated digit in binary. So this, whenever you have a formula, you always want to check extreme cases and ask, is this reasonable? Now, you could also look at what goes on with the Zeckendorf decomposition in the Fibonacci numbers. And what we were able to show is that the probability of a gap of length k, if k is at least 2, is 1 over the golden mean to the k. So as a nice exercise, you should prove that this is a probability distribution. So there are 2 things you have to show if you want to show it's a probability distribution. The first is that things are non-negative. Well, 1 over phi to the k, it's clear that these are non-negative. And the more interesting condition is to show that the sum of the probabilities equals 1. And so I'll leave that as an exercise for you. So what we're going to do now is we're going to prove why this works. We're going to prove this geometric decay, and it shouldn't shock you that the answer depends on the golden mean. And the reason it shouldn't shock you is the Fibonacci numbers are intimately tied to the golden mean, 1 plus root 5 over 2. All right. So there's a beautiful result due to the KKKK that the total number of gaps is basically the number of numbers in our interval. So we're going from Fn to Fn plus 1. That's where the Fn minus 1 is. It's the number of numbers in our interval times n over phi squared plus 1. Or equivalently, if I divide both sides by Fn minus 1, I get the average number of gaps is basically n over phi squared plus 1. Or another way of looking at this, the results I get is the number of summons on average is n over phi squared plus 1. So let's try to see if this is reasonable. We're looking at numbers between Fn and Fn plus 1. What is the maximum number of summons we could have in a legal decomposition?
N over 2.
N over 2. What's the minimum number of summons we could have?
1.
1. And so if you want to think about it, well, it's somewhere between 1 and n over 2. Maybe on average it's the average of them. Maybe it's n over 4.
Why?
No, I'm just saying just to get some rough sense. I take my 2 extremes. It's at least 1. It's at most n over 2. Let's take the average and say maybe n over 4 is a reasonable estimate for how many summons I have on average. I'm just trying to get some rough sense. I know it's somewhere between 1 and n over 2. Let me just try to use the midpoint and see what that gives me. So n over 4 is about 0.25 n. The actual answer is about 0.276 n. So it's actually not a bad, just rough estimate. So you can prove this. I'm not going to bother proving this right now. This is just a nice fact. And this can be proven elementarily. You do not need calculus for this. And now this is where things get a little bit tricky. The biggest problem in probability and combinatorics is to make sure you don't count the same thing multiple times. So you have to introduce really good notation to make sure you don't double count. So Xij is going to note the following. There really should be an n on this to tell us that this comes from looking at the interval Fn to Fn plus 1. But I want to try to minimize the number of indices and minimize just how involved the symbols look. So we often do this in mathematics. When something is fixed and clear from context, we often suppress it just to focus on the things that are really changing. So Xij is going to count how many numbers I have in my interval such that the decomposition of M includes Fi, it includes Fj, but it doesn't include anything between Fi and Fj. So this is essentially forcing us to have a gap between fi and fj. And note that because we have the starting point and the end point, if I choose j to be, say, I plus 5, that's going to give me a gap of length 5, but it's going to be a gap of length 5 starting at I. So the same m could have multiple locations where it has a gap of length 5. And so if I want to calculate these limiting probabilities, well, what I do is I count how many times I have a gap of length k. So can somebody tell me why I have I going from 1 to n minus k?
Just to make sure that all the gaps like with gap like k is counted, right?
Wait, but why doesn't it go all the way up to n?
Well, because if you want to
Because
have
it begin. Yes, sorry.
yeah, because if you want to have a gap k, the largest you can get is n minus k, and the second would be fn. So like, it couldn't go any further.
Right. Well, I could actually have it go all the way up to n, but I would just have those values of x, I plus k just be 0 once I is larger than n minus k. So I might as well not include them. So the numerator is going to just count how many gaps of length k do we have. And if you have a gap of length k, it has to have a starting point, and then it ends 5 things later, or k things later if we're doing gaps of length k. And then if I want to find the probability of a gap of length k, I would take how many gaps are there of length k and divide that by how many gaps there are. And so fn minus 1 is how many numbers I have in my interval. This is how many summons I have on average or how many gaps I have on average. They're essentially the same thing. And so their product is going to be the number of gaps. So all we have to do is calculate this limit. All right. So I want to try to explain how we would calculate this. So what I'm drawing here is f1 all the way up to fn. So if something is filled in black, that means I've chosen it. So it's going to be a summon in my decomposition. So why is fn filled in?
Because you always take the largest Fibonacci number you can get, and because the integer you want to decompose is between fn and fn plus 1, which means that the largest Fibonacci number you can take is just fn, so fn is always taken.
Perfect. We have to have fn because we're looking at numbers between fn and fn plus 1. Why do we have fi and fi plus k?
To make a gap of k.
Yeah. And we said we're trying to count how many numbers have a gap of length k starting at fi. So we have to have fi and we have to have fi plus k.
Professor Miller, can you explain the reason why fn is chosen again? Because I didn't really catch this.
Okay, so we're looking at numbers in the interval fn to fn plus 1, right?
Yes.
So if you're in this interval, then that means you have to have fn as one of your summons. If your largest summon was fn minus 1, you can't be large enough. The best you could be is fn minus 1 plus fn minus 3 plus fn minus 5 plus fn minus 7. And when you do the work, your number is going to be smaller than fn.
Yes.
So because I'm in the interval fn plus 1, I have to have fn as my largest summon.
Oh, got it.
So this is the reason why I like to do the problem this way. I don't look at numbers m from 1 to fn. I look at numbers from fn to fn plus 1. This way, every number has the same first summoned. So I'm basically localizing so that things are of comparable size. Now, if there's an x, that means we don't have that. So because we want a gap of length k, from fi to fi plus k, I can't have any of the summons between fi and fi plus k. Why can't I have fi plus k plus 1?
Because it's right next to fi plus k.
Yeah.
Perfect. We can't have two adjacent things. And that's why we can't have fi minus 1 and we can't have fn minus 1. So what I want to do is I want to count how many ways can I legally choose summons in these remaining possibilities. And we're going to break it up into two parts. We're going to break it up into how many ways can we choose stuff in here and how many ways can we choose stuff in there. So for the stuff less than I, it turns out that there's fi minus 1 choices. And the reason is, let's look at what's going on. We've chosen fi. We don't have fi minus 1. This is the same as counting numbers in the interval fi to fi plus 1. Because if you're in the interval fi plus 1, you have to have fi, you don't have fi minus 1, and then everything else is free. And the number of numbers in that interval is just the difference, which is just fi minus 1. So the number of ways I can legally choose f1 through fi minus 1, does everyone agree that it's just fi minus 1? So this is the key point in the proof. Do we all agree that the number of ways I can legally choose things in here is just fi minus 1? So you have to take off the mute. I can't hear you. Does everyone agree with this, or do we need to talk about this some more?
Let's talk about this more.
Okay. So what does it mean to have a number between fi and fi plus 1? It means we have to have fi as a summand. We can't have fi minus 1. And then with the remaining ones, if we choose a summand, we can't choose a summand next to it.
Yes.
Every number in this interval has a unique representation as a sum of non-adjacent terms. How many numbers are in that interval? Well, it's just fi plus 1 minus fi, which is
fi minus 1, yeah.
because of the rule for the Fibonacci numbers.
Uh-huh.
So this is how many numbers are in the interval. If I look over here, I want to choose my numbers from fi to fi minus 1 in such a way that I can't choose two things adjacent to each other. I can't choose anything more than once. How many ways can I do that? It's the same as asking for how many legal decompositions are there where fi is the largest summand. You can forget about everything from this point onward. This point onward doesn't matter anymore. All that matters is I have fi and I want to choose things legally in here. That's the same as just counting how many legal decompositions do we have where fi is the largest summand. Every choice is going to give me a different number in the interval fi to fi plus 1.
Oh, why is fi the largest summand?
Well, I'm saying I'm just looking at that problem right now.
Okay.
Because we want to have a gap from fi to fi plus k. So we have to have fi as a summand.
Okay, so...
And right now, once we have fi as a summand, we have complete freedom in everything before it, so long as we never choose two things that are next to each other.
I think they're like I minus 3 ways. Is that true?
What do you mean by I minus 3?
Because we cannot choose F2 if we choose, wait. Oh, sorry, I got confused. It's okay.
Wait, no. The number of ways is fi minus 1. Because look, we can't choose fi minus 1. We could choose fi minus 2, or we might not choose fi minus 2. If we choose fi minus 2, we can't choose fi minus 3, but we could choose fi minus 4. So you have to ask, how many ways can we legally choose indices from 1 to I such that we choose I, but we don't choose two things that are next to each other? Well, by definition, that's just how many legal Zeckendorf decompositions are there whose largest index is I.
Okay.
So that's why the number of ways to legally choose indices here so that we don't have two adjacent is just Fi minus 1.
Okay.
Are people comfortable with this? Or at least, if not fully comfortable, just mostly comfortable with something like that? Does this seem reasonable?
Yes. Does it mean that like there are Fi minus 1 choice to like get two numbers?
What do you mean by to get two numbers?
Like now you need to choose two numbers with a gap of like two non-adjacent numbers. So because there are like
I can choose far more than just two non-adjacent numbers.
yeah, so basically it's just a decomposition of a number. So it's the same with Fi minus 1, right?
I think you're close, but just your phrasing is a little bit off. I'm not choosing two numbers. I want to know how many ways can I choose indices from 1, 2, 3, all the way up to I, such that I choose index I, and I never choose two adjacent indices.
Oh, okay. I think
if I phrase it like that, that's the same as saying how many numbers are there between Fi and Fi plus 1, because we know by Zeckendorf's theorem, every number has a unique legal decomposition as a sum of non-adjacent terms. And so we're using Zeckendorf's theorem to say, by Zeckendorf's theorem, every number in this interval, Fi to Fi plus 1, can be written uniquely as a sum of non-adjacent terms where we have to use Fi. And the number of numbers in that interval is just Fi minus 1. So by Zeckendorf's theorem, the number of numbers in this interval is just Fi minus 1. And now if we look at what's going on over here, we have to choose terms. We can't choose two things that are next to each other, and we have to choose the ith term. Well, that's an equivalent problem to just counting how many numbers are there between Fi and Fi plus 1. Because every legal choice we have over here is going to correspond to a legal decomposition of a number between Fi and Fi plus 1. So this is the key step of the proof. Once we get this, the rest of the proof is easy. So if you don't understand, you need to speak up now, and we can explain it some more. So are people comfortable, or do people want to talk about this a little bit more?
Okay, I get it.
It's a lot to see at once and not just sit down and really think about it and absorb it. But it's much easier to talk than just to read. So if you are not clear on everything, please speak up right now.
Professor Miller, can you re-explain like why do we need to find decomposition, like the number of decomposition that contain the gap between Fi to Fi plus k? Is it working towards a bigger aim, or it's just a question we want to solve?
Well, we're trying to calculate what's the probability of a gap of length k.
Okay.
So to calculate a probability of a gap of length k, we need to know how many numbers have a gap of length k. Well, to have a gap of length k, you need a starting point.
Yes, we start with I.
We need to figure this out for each I. So
Yes.
what we're doing right now is this is going to lead, you can see the title of the slide is Calculating xi I plus k.
Yes.
Is we want to know how many numbers between and Fn plus 1 have a gap of length k starting at I. So
Okay.
look at all the ways to choose numbers legally, to choose summons legally, such that we have a gap of length k here. Well, some of the number we know we have to have Fi. We can't have anything until we get to Fi plus k, which we have. And then we can't have the next one. We can't have the previous. We have to have Fn. We can't have Fn minus 1. So we know that as a start. We know it has to look like that. But now we have some freedom. What happens in here? What happens in here? That's what we've got to figure out now. And so the question is, every time we choose something here, we could choose just F1, or we could choose nothing. Or we could choose just F1, or just F2, or just F3, or just Fi minus 1. Or we could choose F1 and F3, or F1 and F4, F1 and F5. We have to go through all those possibilities. And
Yes.
every legal way to choose indices such that we don't have two adjacent ones. And by Zeckendorf's theorem, that's equivalent to counting how many numbers are there between Fi and Fi plus 1. By Zeckendorf's theorem, if you choose a number between Fi and Fi plus 1, it can be written uniquely as a sum of non-adjacent terms. So conversely, if I give you a sum of non-adjacent terms whose largest term is Fi, then that has to correspond to a unique number between Fi and Fi plus 1.
Yes.
So what we do in problems like this is a key idea in combinatorics, is you convert what you want to count to something that's equivalent. So counting how many ways to legally choose which indices we take here is equivalent to just counting the numbers in here. And it's very easy to count how many numbers are in there. It's just right endpoint minus left endpoint. And by Zeckendorf's theorem, that's going to just be the same as how many ways can I choose my indices such that I have to have Fi and I don't have two adjacent terms. So again, it's really important that we understand this because this is the key step.
Understood.
Okay, so let's go down. Let's go person by person and tell me yay or nay. Are you comfortable with this, or do you want us to talk about it a little bit more? And if you are thinking, I'm not sure if I should mention that I'm a little confused, if you're confused, odds are somebody else is. So let's go one person at a time. Tell me, are you happy, or do you want me to talk about it further?
Well, I think I understand it.
Okay.
I understand it.
Okay.
I understand.
Okay. We have one more. Is Heather there?
Yes, I said I am okay with this.
Okay, so we're going to move on. So we understand that there's Fi minus 1 ways to choose things here. What about over here? This is more complicated. Because we now have all these are free. This is not free. And this is taken. So does anybody know how we would count how many ways we can do things in there? Is it similar to at least what was going on over here?
Is it Fn plus I plus K?
No, but you're on the right track. Fn plus I plus K is too large, right? We have at most F minus 1 ways of choosing things overall.
Oh, is it Fn minus I and minus K?
It's something like that.
Oh, okay.
What's going on here? See how this one is free? Ignore everything from here to the left. Just focus from here onward. It's like we're playing a new game now. I can just shift all the indices down. So I'll take this and I subtract I plus K, and this is kind of like now my F1. And then the next one would be like an F2. And this would be Fn minus I minus K. And so it's very similar now. So if we just look at, now I want to go from F1 to Fn minus K minus I plus 1, we can then ask the same game how many things there are. The actual details, the actual algebra, I don't really care about. I just want you to see that it's essentially the same problem. We just have to play some index shifting games. And actually, we have to be a little bit careful. It's not I plus K plus 1. it's I plus k plus 2 is the first one, because we can't use this one. So we have to shift, we have to subtract I plus k plus 1. And that's why fi plus k plus 2 goes down to f1, and this goes down to fn minus I minus k minus 1. But since we're subtracting the minus 1, now becomes a plus 1. And now we want to know how many ways are there to choose summons legally from here where you have the last one. Well, that's just going to be fn minus k minus I plus 1 to fn minus k minus I plus 2. So I think there might be a typo. I think this is, I think it's supposed to be a minus 1, not a plus 1. Yeah, that should be a minus 1. So now I claim that the total number of choices is just the product. I can choose something legally here in fi minus 1 ways. I can choose something legally here in fn minus k minus 2 minus I ways. So since these are independent choices, the number of things that I can do total is just going to be their product. So are people roughly okay with how we got this? And again,
Yes.
again, unfortunately, some small typos. This should be a minus 1, not a plus 1. But what's nice is the analysis on the right is really the same as the analysis on the left. All that we have to do is just shift the indices down. And this is why we talk about gaps between indices and not gaps between the numbers. We can now just play these shifting games. So we actually have an explicit formula for how many numbers between fn and fn plus 1 have a gap of length k starting at I, of the ith summoned. And now what do we have to sum this over? So this is going to give us a gap of length. How many numbers have a gap of length k starting at I? What do we have to sum this over?
Total gaps.
Well,
So-
we'll divide it by the total gaps, but what do we sum it over?
Like for every possible I, like
We have to sum it over I now. So we want to sum this over I. So we put in our formula. And it turns out that there is a formula for the nth Fibonacci number. Have you seen Benet's formula?
Yes.
Yes.
So Benet's formula is that the nth Fibonacci number is 1 over root 5, the golden mean, 1 plus root 5 over 2 to the n, minus 1 over root 5 times 1 minus square root of 5 over 2 to the n. So when you plug that in and you use the geometric series and you just do some algebra, you end up getting the following result. So it's amazing how things simplify very nicely in the limit. Another way to view things is the nth Fibonacci number is almost the golden mean to the n, or 1 over root 5 times the golden mean to the n. So if I look at this, this is going to look like 1 over root 5 golden mean to the n minus k minus 2 minus I, and this will be 1 over root 5 golden mean to the I minus 1. So the 2 root 5s reinforce and give me a 1/5, and then I get an n minus k minus 2 minus I plus I, so the i's cancel, so like a minus 3. I'm going to then sum, I goes from 1 to n minus k. You know, if k is fixed and n goes to infinity, that's going to roughly give me an n, which cancels with the n down here. You'll see you're going to get a phi to the negative k, which is going to be very nice. This one over here is going to look like a 1 over root 5 golden mean to the n minus 1. So you can just, when you do the algebra and just try to get some rough sense, getting 1 over phi to the k at the end of the day is actually pretty reasonable. And again, I'll leave this as an exercise for you. You can just try to simplify it by just assuming that the Fibonacci numbers are exactly 1 over root 5 golden mean to the n for the nth Fibonacci, or you can use Benet's formula and just do the algebra. when you see proofs like this, you really want to try to get a sense of where do you have to think and be clever, and where do you just have to plow through the algebra. And from this point, once we get to the formula at the top of the page, we're now down to just plowing through the algebra. We've done the thinking. The hard part was getting to this formula. And now we actually have Benet's formula, so we can use that to simplify this. Okay, so this completely resolves the probability of gaps from the Fibonacci's. There's lots of ways to do gaps. This is the easy way, where what we are doing is we're looking at all the gaps simultaneously. A much harder thing to do is choose a specific number and look at the distribution of gaps from that specific number. Well, some numbers won't have many gaps, some numbers will have a lot of gaps, most numbers will be close to the average number of gaps. And so with a lot more work, you can handle looking at a specific number. For us, we're going to focus on the average by just looking at all the gaps together. In mathematics, the more you average, the easier things are. And so the way you should think about it is each m, each number between fn and fn plus 1, has a sequence of gaps. It has some gaps of length 2, some gaps of length 3, some gaps of length 4. And what we do is we put them all in a giant bucket. And then we just count how many of the gaps are of length 2, how many gaps are there of length 3. A much harder problem is choose a specific value of a specific number between fn and fn plus 1, and then for that number ask what fraction of that number's gaps are 2, what fraction of that number's gaps are 3. Essentially, it means we don't have a nice denominator like this as well. All right. So I want to now shift to starting to get to the problem I want us to look at this summer. We've talked about trying to generalize the Zeckendorf theorem to come up with new recurrence relations. And we want some kind of combinatorial meaning to what we're doing. And we want something that's two-dimensional. So we're going to look at what's called simple and compound jump paths. So up until about a month or so ago, there were only results for simple paths. My students and I just finally finished proving similar results for compound jumps. So as it's getting late, I'm not quite sure exactly how far we'll make it this time. You can prove Gaussianity for the simple jump paths, and we just proved it for the compound. And the future research question for you guys is going to be something that no one has really looked at before. It was only briefly started last summer, is looking at the distribution of gaps in these simple paths. All right. So we've talked about a Zeckendorf decomposition. We've said this many times. Every number has a unique decomposition. We've talked about using greedy algorithm to do it. All right. So we want to construct a two-dimensional sequence. We tried to do this before with a Fibonacci quilt, and there was some geometry there, but it turns out you can collapse it. I want something that's really fundamentally two-dimensional. So I'm going to have two indices. So I'm going to set my first term to be 1. And then for every number, I'm going to do a path on lattices. So I'm going to look in the upper right quadrant. So I'm only going to look at points x and y where x and y are positive numbers. And here's the rule. If I have some number, say 5, 7, the next number I choose, I have to move both down and left. Okay? So when you're walking, you always have to walk down and left. You can't walk just down, you can't walk just left. You definitely can't walk up or right. So for example, let's start over here with the number 1. And we're going to fill in our numbers going diagonally like this. So I want to have 2. Okay. Okay, so actually for the first one here, I'm allowing myself to move just left or just down. I just can't move right enough. I apologize. So this is the harder problem. This is the compound path. This is the one we just finished doing, so that's why I've included the slides here. Can I get the number 3 starting here without ever going up or to the right? How could I get 3?
2 plus 1.
2 plus 1. Can I get 4?
No.
No, so I have to add 4 as my next number. So I've now finished this diagonal, so I now come here. Can I get the number 5?
1 plus 4.
1 plus 4. Actually, let's do 4 plus 1 falling downward. Can I get 6? No. So I have to add 6. Can I get 7? Yes, 6 plus 1. Can I get 8? Yes, 6 plus 2. Can I get 9? Yes, 6 plus 2 plus 1. I can't get 10. I can get 11. I can get 12, 10 plus 2. I can get 13, 10 plus 2 plus 1. I can get 14, 10 plus 4. I can get 15, 10 plus 4 plus 1. But I can't get 16. I can't do 10 and 6 because I can't go to the right. So I have to add 16. I can get 17, 16 plus 1. I can get 18. How do I get 18? No, I can't get 18. So I have to add 18. I can get 19 now. I can get 20. I can get 21. 18 plus 2 plus 1. I can't get 22. Is there another way to get 20 other than 18 plus 2?
16 plus 4.
16 plus 4. So we see, very similar to the Fibonacci quilt, that we've lost uniqueness. And so we can keep filling in the table like this. And you can ask, is there a nice rule for the terms in this table? And then if I start at some number over here, I can ask, how many legal decompositions are there where I always move either left, down, or left and down? Okay, so the compound path allows us to move only down and to the left, and you are allowed to move just down or just left. The simple path requires you to always move both down and left on each step. So we can count how many paths there are from AB down to 0, 0. And so I'm not going to go into too much detail with all this stuff as it's getting a little bit late. But we want to count how many paths there are. It turns out that in 2 dimensions, it's not so bad to count how many simple paths there are. The compound paths is a little bit more involved. And then we're putting in this extra point of 0, 0 that we just have to end on. It's just technically convenient to force ourselves to end at 0, 0. And again, when you're seeing math live, it's very hard to process math live. You want to be able to just sit down and play with it for a while. So what we want to do is we want to count how many paths are there from some point AB to 0, 0 with k steps. And so we can introduce some notation for that. These are now all theorems. We've solved them, so we're not going to really be looking at them. The simple path, as I said, means you have to move both down and to the left. And it turns out this is a lot easier to analyze. So we can count how many simple paths there are. That'll be SAB. We can calculate how many simple paths are there of length k, and we'll call that TABK. So we can get certain results about how many such paths there are. And it turns out that there's a really beautiful formula for how many paths there are starting at AB and having k steps. And it's A minus 1, k minus 1 times B minus 1, k minus 1. So A minus 1 choose k minus 1 times B minus 1 choose k minus 1. It is wonderful that we have such a simple closed expression. So if you think about what is this, the first factor is the number of ways to group A objects into k non-empty groups. And the second one would be the number of ways to group B objects into k non-empty groups. So clearly we just take their product and they're independent. So let's think about what's going on. If I want to have k steps, and in every step I have to move both down and to the left, then I have to make sure that the sum of my steps adds up to A when I'm talking about moving the left and right, and B when I'm talking about moving the up and the down. And I'm not going to go into the details, but if you're interested, I can give you the paper to read. The analysis is extremely similar to what we were doing before with the cookie problem. It's the cookie problem just coming in again. But why are things different than the cookie problem? You know, the cookie problem, how many ways are there to divide C cookies among P people? It was C plus P minus 1, choose P minus 1. Whereas here, it's A minus 1, choose K minus 1. Does anybody know what the difference is between these two problems? Something has to be something that's forced on us in the Fibonacci case that's not forced on us now. So what must be true with our Zeckendorf theorem, with our Fibonacci decomposition? What must be true about our summons?
They're non-consecutive.
They're non-consecutive. So if I have A numbers, I have to choose the last number because we're starting at the point AB. So I now have A minus 1 numbers. And I have to choose K minus 1 stopping points because I want to have exactly K summons. So I have to choose K minus 1 places to stop. How many ways are there to choose K minus 1 stopping points from A minus 1 candidates?
It's just A minus 1, choose K minus 1.
Yeah, it's just A minus 1, choose K minus 1. But that's the definition of choosing. So that's where this factor comes from. And that's why it's so much cleaner in this case than in the Zeckendorf Fibonacci case. Because we have the last summon, we have A, and now we just have to choose K minus 1 of the A minus 1 points.
Okay.
If we did the compound path, it would be much, much harder. And the reason it's harder in the compound path case is because it's possible that you only move in one direction. And you've got to then be careful about how you then deal with things. So it's a lot of inclusion, exclusion, but it can be done. And so this is just a small plot, just looking at, from the point 10, 10. And already you can see it's not that far off from a Gaussian. The shape is not so bad with a small number of data points. All right, so we want to show that it converges to a Gaussian. So this is not going to be one of the projects for the summer, so I'm going to do this really fast. So we want to look at what's going to go on for various choices of K. So we have a simple jump path. And now we're going to study the special case when A equals B, just to make the algebra a little bit simpler. So the first thing is to calculate the mean number of steps. And it turns out it's basically n halves. So we need to calculate the following. It's sometimes a little bit convenient to shift what you're studying. So if you notice, instead of doing n, I'm doing n plus 1, n plus 1. And the reason is if you look at the formula we have A minus 1 and B minus 1. Wouldn't you like to get rid of those minus 1 up top? We can get rid of those minus 1 up tops if we just let A and B equal n plus 1. We might even want K to be K plus 1 just to make things a little bit nicer, but that's fine. We'll keep it as K minus 1. So this is going to be n choose K minus 1 squared. We should, if we want probabilities, we should divide by the number of paths, but that's fine. You can always put that in later. And we just want to evaluate sums like this. So it turns out that there are techniques for evaluating these sums. Since I don't know yet if we're going to need this for what we're doing this summer, I'm going to hold off on doing too much about how to evaluate them. It's just there are techniques for evaluating stuff like that. They're not calculus-based. That doesn't mean they're easy. It just means the prerequisites for it is at the level of binomial coefficients. And this will allow us to calculate the average number of steps. You can calculate the standard deviation. So if you've seen statistics, we've talked a little bit about fluctuations. The quantity is a little bit more involved. But again, the standard techniques work. You just split it into a bunch of sums, and each one of them can be handled. And now if we want to try to prove Gaussianity, we count how many paths are there. We're going to do paths of length k plus 1. From the point n plus 1, n plus 1, we divide by the total number of paths, and we have a ratio of binomial coefficients. And now we just use Stirling's formula eventually. We plug in, and we now start doing a lot of algebra and simplifying things. And so I'm not going to go through the details of the algebra, but eventually when the dust settles, you end up that it becomes a Gaussian. So it's important to keep a sense of where is the idea and where is the algebra. The key part that makes all of this work is that we are able to find an explicit formula for how many paths are there of length k in our simple path case. And it's a product of binomial coefficients. And there's a lot that we can do with products of binomial coefficients. There's a lot of formulas for them, and it turns out we can get a nice, simple closed form expression. It is not always the case that you can get a closed form expression. But we are very fortunate here. For the compound path problem, it's much harder. So our goal for the summer is going to be to try to understand what's the distribution of the number of paths. And there's a lot of complications in that. So I don't really want you thinking about the research problem yet. I just wanted you to have some sense of where we're going before we get too deep into the summer. So you have some idea of what to be listening for as we do all of our conversations. And then for the next time, we'll talk a little bit more about how you can attack and analyze problems like this. But we did a lot today. We figured out how to prove what the limit is for the probability of a gap of length k for the Fibonacci's and the Zeckendorf decomposition. And we saw it was a really nice answer, and the answer depended on the golden mean. We saw a real two-dimensional generalization coming from the lattices. And then the hope is that we can somehow generalize these arguments. And we saw it was a little bit involved to just figure out how many ways are there. And a good way to do the counting was this quantity xi, I plus k. And so if you have a gap of length k, it has to have a starting point. And this allows us to make sure we don't count the same gap twice. But the same number could have a gap of the same length multiple times. And it turns out when we do the analysis there, we ended up getting a product of Fibonacci numbers, and that product turns out we can evaluate it. All right, any quick questions now? Okay, I'm going to go work then on trying to get the video posted online. And I will wish you all a great evening, and we will talk again in the near future. Have a good
one. See you.
Take care.
Thank you.
Okay, bye-bye.